Thank you, and welcome to this acoustic seminar webinar, which is the second one of this year, 2014. And our topic today is acoustic simulation of duct intake and exhaust systems. Very briefly, our agenda. So first, we start with an introduction to duct acoustics, and in particular, intake and exhaust noise issues, including pipe noise and shell noise issues. Then we will see how we analyze these two problems using the Actron software. And following that, I will give a short demo in Actron VI, which is Actron graphical interface. And the demo will be about a Muffler sound transmission loss problem. And that will be followed by the Q&A session. So first, let us, before we start the technical presentation, let's review very shortly some industries that could have the noise problem related to duct systems or intake and exhaust systems. Now, in automotive industry, so clearly, which will be the main topic of today, we have duct acoustics in both intake and exhaust lines. For example, the muffler transmission loss or the air filter acoustic behavior are all subjects of today. Also, in other industries like consumer products, for example, in the vacuum cleaners, we also have duct acoustics. For example, in this duct of this vacuum cleaner. In other industries like construction, we consider duct acoustics, but in a grander scale. For example, acoustic propagating in the air conditioning systems in the buildings, or this example, which is a very specific one, it's about the test facilities that is designed for testing the performance of aircraft engine. But we see we have ducts and pipes that are of grander scale. Of course, in other sectors like shipbuilding and aerospace, we have similar problems, which all fall into the category of duct acoustics. So today, many of our applications that I will show are in the automotive industry, but the principle of numerical method or engineering method are quite common in duct acoustics among all these industries. So let's take a look at the problem description of intake and exhaust systems. So today, of course, the acoustic efficiency of intake and exhaust systems are of increasing importance in the design process of quiet vehicles. And the acoustic wave propagation in those systems is called in-duct, in the sense that the entire line is made of complex components like the mufflers or the catalyst in the exhaust system. And these components, they are connected by pipes or ducts. The total noise produced by an complete intake or exhaust line is the sum of two main noise contributions. The first one is called pipe noise. So the noise source here of the pipe noise is typically from the engine pump. And the pipe noise is an air-borne noise production, which means the acoustic waves propagate through the interior volume of the lines and the components. And this propagation will go through the entire system until it is propagated out of the outlet of that line. And flow-induced noise is also occur in the pipe and the duct systems. The second contribution is the so-called shell noise. In this case, the propagation is a solid-borne one, and the noise source is typically the vibration of the engine block or the vibration to any vibrating structure. Sometimes the pipe noise is studied alone and separately from the shell noise, and this neglects the vibration of the structure. And in that case, the interior air volume, is a pure acoustic problem. However, this is a assumption of the reality, because in reality, these two contributions, they also interact with each other. So the interior acoustic wave, it generates vibration of the shell, and in return, the shell vibration also is also the source of interior acoustic waves. Now let's take a look at the pipe noise, and I'll give you a quick view of the action features that support the analysis of pipe noise. First action is a 3D finite element solver, and it can solve the acoustic propagation in complex systems of complex shapes. And this distinguishes the action capability with some 1D numerical tools, which can solve only the simple shaped problem like this one on the left, which is the expansion chamber. While in action, we use finite element 3D method, and we can solve complex shapes like this muffler on the right. And moreover, the frequency range of the analysis is not bounded by the 1D assumption. We'll come back to that point later on. Action features acoustic duct mode component. So this duct mode, they are used to inject a realistic acoustic source, for example, a engine pulse, into the line system. And the duct modes, they are also used to provide perfect non-reflecting boundary conditions for anechoic conditions for any reflected wave to the upstream of the system. In action, we have infinite elements, infinite acoustic elements, or adaptive perfectly matched layer, or APML. So these are two alternative methods that we use to simulate acoustic radiation at the outlet of the line into the ambient air. And pipe noise models can also take the low heterogeneity containing the temperature gradient or any gradient of local low velocity into account. So these two components will modify the acoustic propagation that as we will see in a slide later on. Porous finite elements can also be included to represent absorbing materials such as rock wool or mineral fibers. The perforated plate or perforated duct can be modeled also in action using semi-empirical transfer admittance formulation. For the analysis of an entire line, a transfer matrix method is available in action. And this is a very useful method in the design phase to quickly assess the effect of any modification on one particular component in the entire exhaust or intake line. Finally, the flow-induced noise can be solved by action by its aeroacoustic module combined with commercial CFD tools. Now we will review some of these features technically in the next couple of slides. So first, what are the duct acoustic modes? Acoustic duct modes components are a mathematical representation of semi-infinite acoustic duct. First, to understand what a duct mode is, it is important to recall that in a typical duct or a pipe, the total acoustic pressure inside that duct is the sum of an incident wave propagating downstream, in this case to the right, and the reflected wave that is propagating upstream back to the left. And in any case, both the incident and the reflected pressure waves can be seen as a mathematical superposition of acoustic duct modes. So let's take an analogy to structure dynamics, as we know that the vibration of, for example, a plate is a superposition of many of the modes of that plate. So similarly, in acoustics, the pressure distribution across cross-section is also a superposition of the acoustic duct modes. Now, with acoustic duct modes, in a certain cross-section, at low frequencies, only the plane wave can propagate. So the first picture here shows a plane wave propagation. We also call the plane wave plane mode a zero-order mode. As the frequency increases, or as the cross-section gets larger, then acoustic duct modes of higher order will also be able to propagate. So the second image and the third image shows the pressure field of high-order acoustic modes. Now let's apply the acoustic duct modes first into the sound transmission loss analysis of a component. Now we're analyzing a muffler problem here, and we are interested in the sound transmission loss, or the TL index of this muffler. And to do that, we will apply at the inlet of that muffler a incident wave through the acoustic duct mode. And this wave will propagate through the muffler and transmit it from the outlet to the ambient field. And because of the complexity of the geometry, some wave is reflected in the system and will transmit back upstream to back to the system. The sound transmission loss that we will calculate is a ratio between the incident power at the inlet and the transmitted power going through the component. And we simply apply a logarithmic scale to that ratio to calculate the sound transmission loss. So this slide shows very typical results of a transmission loss in dB. So we can see in the curve, we have two frequency regions. In lower frequencies, we have this periodic behavior, which indicates that we have plane wave propagation throughout all the system. So we have plane waves not only in the inlet on the outlet, but also through the muffler volume. And this is not true anymore when frequency goes up. Here as this picture indicates that we have the clearly plane wave at inlet and outlet, but the propagation in the muffler volume is not planar anymore. So with the 3D solver like Actron, we can not only solve the low frequency problems, but also the higher frequency problems. In simulation of duct acoustics, many times we will also need to take the flow heterogeneity into account. So we are talking about two types of flow heterogeneities. The first one is the temperature gradient that we need to consider many times, especially in automotive exhaust systems. So a local temperature field or pressure field or density field of the air, they will impact the local speed of sound in the air, and which will consequently modify the acoustic propagation through the pipe or the duct. The second effect is the mean flow velocity, which also modifies the acoustic wave propagation, and this is known as a Doppler effect. In action, when we need to take the flow into heterogeneity into account, we will typically run in the first step a RANS CFD analysis, which is a steady CFD analysis that output the flow velocities and the temperatures or pressure or the air density, etc. In action, we also have an integrated flow solver that can solve the flow velocity and the temperature field. And in the second step, we will map through the action ICFD utility, which is the interface between action and CFD result. So through this utility, we will be able to map the CFD static, the CFD result onto the acoustic mesh, and therefore that flow heterogeneity is taken into account into the acoustic simulation. Now this slide shows the difference of transmission loss on the same muffler between the case where we consider the temperature effect and the case where we just ignore that effect. We see that there's a significant influence by this temperature field, which is the temperature was higher at the location where we are closer to the engine, and the airflow cools down to the muffler when it goes out through the muffler to the exhaust outlet. Now, in the muffler design, a typical component or typical material that we use today is the porous material, which provides acoustic absorption. So porous material are the foam or rock wool or fibers, etc. And here we are looking at an industrial silencer, which is quite a big one and is composed with several volumes. So here in the central volume, we have a fiber material, and on the expansion volume outside, we also have porous material filled, and the air channel is this red one between these two porous domains. In action, to accurately simulate the acoustic behavior of a porous material, we are based on the Biot formulation developed by Mr. Biot, and it is global. It is a global formulation that assumes global and homogeneous properties of several groups of properties on the material. So we'll see that with the Biot model, we are dividing the material properties into different groups of properties. First, the foam skeleton properties, which include the Young modulus of the skeleton, the density, the Poisson ratio, etc. And the fluid properties, which is basically the properties of air. And a group of properties that describe the interactions between the skeleton phase and the fluid phase. So these properties are the tortuosity, flow resistivity, and porosity, etc. And to most accurately model the porous material in action, we have the complete Biot model, which is a poroelastic formulation that models all these, takes all these properties to account. Otherwise, if we do not have all that properties available, we can also use some simplified models like this Mickey model, which is an semi-empirical model, or the rigid Porous that assumes that skeleton is rigid, or the lumped Porous that assumes that skeleton is a soft one. And with simulation on Porous material, we can output not only some local displacement or acoustic pressure in the Porous material, but also a very interesting indicator is the energy dissipated by the Porous material. So this will give some insight on how material is damping acoustic power. In modern mufflers, another typical design is the perforation. So either perforated plate or perforated duct. So a perforation is a thin sheet of plate or a circular duct that has some holes in formation, as it is shown now on this picture. And to simulate the acoustic behavior of a perforation, of course, we can, in the meshing step, we can mesh the holes of the plate, but this is not an efficient method. But instead, in action, we can use a equivalent transfer admittance method to establish a relationship between the two sides of that plate without meshing the holes in the plate. So a transfer admittance is characterized by a matrix that links the acoustic velocity and acoustic pressure on each side of the perforation. And the factor A here in the matrix can be calculated using a established formula that is called the Michaels formula, which is also implemented in action. So basically, we just need to provide some geometrical properties of that plate. For example, the distance between the holes, the size of the hole, or the thickness of the plate. So action can calculate this transfer admittance for you. So the advantage of using the Michaels formula instead of meshing the holes, it's first, of course, it is time saving because we don't need to do the tedious meshing, and consequently, we don't need to refine the volume mesh close to the holes because we're not meshing the holes. And also, the Michaels formula takes into account the dissipation through the viscous effect in the holes. So it is accurate modeling. Here we are showing a validation of the Michaels formulation. So we are having here a simple expansion chamber containing a central volume and the circular volume outside, and these two volumes are separated by the perforation. And we see that the transmission loss through this expansion chamber is predicted by action numerically, and this the correlation between measured data is a very good one. Okay, so we have reviewed some techniques to model the individual component in an intake or a exhaust line. Now we are interested to, at this step, to analyze the entire line that is composed with several components and are connected. These components are connected by the duct and pipes. So we're introducing here a transfer matrix method, or the TMM. So idea of TMM is to divide the whole system into several subsystems. So typically, a volume component will be a subsystem. And any subsystem is analyzed using finite element 3D solver in action, and their individual transfer relations between the inlet and the outlet of that component is calculated. And the TMM integrated in action will assemble all the individual transfer matrices into a global transfer matrix, and this will allow us to calculate the transmission loss of the entire line. We can also introduce the real source at the inlet. For example, we can provide a source amplitude and a reflection factor at the inlet, and apply apply an infinite element at the outlet to calculate the free field acoustic propagation. So we see clearly some advantages of the TMM method integrated in action. So first, all the sub-components, they are still solved using the same solver. So all the complexity that we have introduced just now can be taken into account. For example, the flow, temperature effect, the acoustic treatment, porous material, perforation, and also the shell noise that we will see later on. They can be modeled in each individual component. And the action TMM also overcome the frequency limitations, the 1D limitation that is present in many classical TMM implementation. And from a design point of view, if we change the design of one component, we don't need to recalculate the whole line, so that design change can be done efficiently and quickly. Very quickly, I will show you two validations of the one from the component level of the intake system. So this one is a air cleaner component, and the project was performed by Suzuki several years ago. We are interested in the sound pressure level at a outlet point of that air filter, and the source is a unit source applied on the inlet duct. And we see that the experiment and action analysis gives us almost perfect correlation on that air cleaner problem. And second is a system modeling. Here we are validating the TMM method using the finite element modeling. So we are looking at this motorcycle muffler from Suzuki, and we see here in this main muffler we have quite complexity. So there are several stages in the muffler, and we have pipes and ducts going through, and there are perforation and porous material inside. And in this case, we divide this line into two components. One is three components. One is the inlet speaker excitation, and one is the muffler itself. The third one is this small sphere, which represents the free field radiation outside. And we see that the TMM method gives us the same result as if we calculate the whole system using completely finite element based method in action. And of course, here the advantage of TMM is that we will have a significant time gain compared to the entire modeling using FEM. Okay, so we have been talking about sound propagation in the duct, and the source is often from engine pulse, for example. Now, in this slide, we are looking at another type of source, which is a flow-induced noise inside the volume. So apart from source from upstream engine, we can also have this flow-induced noise that is generated by turbulent flow inside any volume or duct system. Now, to solve this flow-induced noise, we need to go through a two-step analysis. In the first step, a transient CFD analysis will solve the unsteady flow using a LES, so large eddy simulation, or DES, the detached eddy simulation. And in the second step, action aeroacoustics module will read the CFD result and map them on the acoustic mesh. And action will perform this acoustic analogy that transforms the CFD flow result into the equivalent acoustic sources. So behind the implementation, we have actually gone through this process from the Navier-Stokes equation that governs the flow, the flow propagation, to the wave equation that governs the acoustic propagation. And this is done using the acoustic analogy. So in action, we have the light hill or the moorings, two types of acoustic analogies available. And when the aeroacoustic source is calculated, action acoustic solver will be able to simulate the propagation of that source into to the exhaust outlet. So the process is really divided into two tracks. So on the left, we have the fluid dynamics, CFD track, and on the right side, we have the acoustic track. And the fluid dynamics will provide to acoustic analysis at the very end of its of the CFD computation. The CFD result will be provided to the acoustic simulation as the acoustic sources. So on this slide, we are showing a validation of the flow-induced noise, and it was a project that Visteon performed a couple of years ago. So Visteon is a automotive supplier that makes the air conditioning systems. In this problem, we are interested in this turbulent noise created by this duct. So as we can see, in the first step, the fluent solver solves the CFD result. So here we are looking at the result in one time step, but in reality, we need that result in a large number of time steps. And those results will feed the action acoustic solver for the acoustic radiation. As we can see here, we get a quite almost perfect correlation between the measurement at this microphone position and the simulation. So the frequency range is from 0 to 3000 hertz. Okay, so that was the topics of pipe noise. Now let's take a look at shell noise. In order to solve shell noise, we will need structure elements. Now, although we position action as a acoustic solver, it is acoustic module of the MSC software, but also action has quite rich structure modeling capabilities. For example, for shell modeling in action, we have two types of shell formulations. One is the thin shell formulation. So on the thin shell element, the thickness of the shell is not meshed. The thickness is actually a property that belongs to the shell element. There's also a solid shell formulation, and the solid shell is useful when we have sometimes the multi-layer problems. For example, we can have a air conditioning system that is baked with first a solid material, and that is surrounded by some thermal layers or some acoustic treatment layers, and all these multi-layers could be modeled by this multi-layer shell capability in action. And there are also other interesting capabilities like this pre-stress feature, which will model the stress initially generated in a shell when we have very significant pressure difference inside or outside that shell. To model the shell noise, we also need to many times consider the fluid volume inside and outside that shell component. And for that purpose, we will need the incongruent mesh coupling. That is a quite convenient feature to model multiple domains. So typically, the shell element can be meshed separately from the meshing of the interior volume and from the meshing of the exterior volume. So in the interior air, we can introduce the air properties, which is has its own density, speed of sound, and temperature. And outside, we'll have another set of properties. And all these three domains, they are connected using the interface coupling capability in action. So we don't need to mesh to have the node shared mesh through these three components. So this is a small example of the shell noise analysis. So as we've seen previously, here we have the mesh of this shell component and the interior air together with exterior air. And acoustic excitation could be acoustic one. So the wave propagating in the internal air volume. And excitation could also be the mechanical load from the mounting point that is applied on the shell structure. And here on the bottom of that slide, we see the acoustic pressure field that is calculated internally in the cavity and structural deformation. These two results, they are strongly coupled, so we are solving a strongly coupled vibroacoustic problem. And it's quite interesting to analyze also the energy balance of such a system. So the idea is to say that, look, I have a unit excitation, which is represent 100% of energy, and I would like to see how much of the energy is distributed into different channels. For example, we'll see that some energy is transmitted to the outlet, some energy is reflected back to the upstream, and some energy is dissipated in the shell because the shell is vibrating, and some energy is radiated by the shell vibration into exterior air field. And this gives us an idea of the energy balance, and which is of course also frequency dependent. Okay, so that was my main presentation of today, and now I will give you a small demo on in-action VI for the Muffler transmission loss problem. Okay, so now we are looking at the graphical interface of action. So it is called action VI, and this is the interface where all the pre-processing and post-processing tasks are done related to an action simulation. Now, I've already prepared the model, and I will explain to you each of the components in this Muffler model. So we see a 3D volume, which is the Muffler volume, and a inlet surface, and one outlet surface. We want to calculate the sound transmission loss through this muffler from the inlet to the outlet. Now, to do that, I need to first build in the analysis an acoustic component. And this component will be the type of fluid, finite fluid, and it refers to a material which has properties of air, standard air, with this speed of sound and fluid density. Okay. And I need to apply the acoustic duct mode both in the inlet and outlet. First, at the inlet, I'm using this modal duct, okay, with this circular shape, and the geometry properties need to be specified, but it could be calculated automatically using these buttons to specify to the solver where this surface is located, and its radius is also calculated using these buttons. That was quite convenient. And we will apply through the mode a excitation that goes through the propagating direction. So the first mode is the excitation, and it has a pressure amplitude of 1. And then we need to set up a anechoic condition for the reflected waves, and this -1 indicates that -1 and free condition means that all the reflected waves they are propagating freely back to the upstream. And here on the outlet, I will set similarly a duct mode, but this time with only one propagating mode, and going to the downstream. So direction 1 indicates that the mode is going outside of the muffler, and we have a free condition, which means anechoic condition is applied on this surface. And we are setting up a frequency response analysis through a frequency range from 10 Hz to 2000 Hz with a step of 20 Hz. So this model has been run previously in action, and I will here simply, for the post-processing, import the result calculated by action. Here we are first looking at a 2D plot. So in this result file, we can find this inlet duct and outlet duct separately. To plot the transmission loss, we just need to go through several very simple steps. So first, in the x vector, which is this horizontal axis, we will bring the frequency index here. And in the y data vector, I will choose the transmission loss indicator among many available post-processing indicators here. And I will bring the corresponding incident energy and the transmitted energy into this composed TL indicator. And then I will simply update this plot and gives us the transmission loss, which is a frequency-dependent curve, and the y-axis is on the dB level. And we see again that in low frequencies we have periodic behavior, and this is a typical plane wave behavior. And in higher frequencies, we see this complex TL behavior, which means that we are not on the plane wave assumption anymore. Now this can be verified by the color map. So I'll come back to the main window here, and I imported the pressure field and to plot the map of the pressure in the muffler. So here we are looking at this pressure, acoustic pressure through the muffler, and we see it's a frequency dependent one. To look at the interior of that muffler, I will apply 2 cut planes and change the orientation of one of them. So we see a 2 orthogonal cut planes, and acoustic waves in this muffler is clearly visualized. So as we have seen that below about 1000 or 1200 Hertz, the acoustic propagation has a plane characteristics, and this can be verified in the map result. And as we go up to higher frequencies, it's going up to higher frequencies. As we go up to higher frequencies, for example, 1500 Hertz, we see that the propagation is not plane, it's not planar anymore, and this explains the high transmission loss, because the natural mode of this semi-cavity is on the opposite direction. The pattern is on the opposite direction of the intended acoustic propagation, and this will not favor the acoustic propagation, which result in a higher TL around that frequency. Okay, so this ends my demo and presentation. And with that, I would like to thank you for attending today's webinar, and we can proceed to the Q&A session.